Alright, let's go through a couple notes here. I have you for about a half hour or so. So we'll just we'll start with the section that we're in. We're in section 10.4. This is talking about inscribed angles. This is something we talked about yesterday, so let's go through those two vocab words. So if you were not here, if you weren't quite paying attention, you didn't quite understand it. Here's what we talked about. In a circle, previously, we've always done, like, especially on this page 718 stuff that was due today, we've always talked about central angles. This angle right here in the center of the circle, right? That's the perfect center. This angle, whatever it is, let's say it's 15 degrees. That angle is the same as how they label the arc on the outside, right? That's called the central angle. The central angle has the vertex right at the center. The two rays that make the angle are actual radii of the circle itself, okay? So, those are the parts that we have, okay? Now, what we're doing is we're taking that angle and we're moving it across the picture like that. It's no longer at the center. It doesn't even have to touch the center. Maybe the center is right here. It doesn't have to. That's the difference. That's the new step we're going into, okay? And what we talked about yesterday is we did two theorems. The two theorems that we talked about, 10.6 and 10.7, talked about how do we find like this angle right here? Or how do you find the arc if you had that angle? Because previously, you know, the angle was the same as how they labeled the arc, and that always threw off people that they put the angle on the outside of the circle. Well, what we talked about is if this angle was, let's say this angle is 15, the arc that's across from it, because now this is called an inscribed angle, it's not a central angle, but inscribed, the arc across from it is doubled. So this would be 30. That's what we talked about yesterday. That was the examples we were doing. That the arc is always double of whatever the angle across from it, or vice versa. The angle's half the arc. That was, I think, the exact wording that we used in the theorem. So 10.6 said, if you have an angle that's inscribed in a circle, the measure of that inscribed angle is half the arc that it intercepts. So it's half that arc. The intercepting arc is the arc that is in between the rays of the angle. So that's an intercepted arc. Or what I think the word I used yesterday was like the word subtended. The word that some college textbooks, but intercepted is the most common word that you'll see. Okay, questions with the two concepts we've been using. I think the last example we did yesterday was if you were to put the angle in multiple spots. Like let's say you had an arc over here. Let's call this arc 48 degrees. So that was my arc. And you had inscribed angles looking at it, just like this last one, this is 24, it's half the arc that it looks at. But we could also put it going the other way. We could have it go up here to this corner, and this would be another angle. This would also be 24. It's always half the arc that it looks at. Even though we have it going to different locations, they're still looking at the same arc. So they're still half of it, whatever it is. Questions about that theorem? That was theorem 10.7. So two arcs intercept the same, or two inscribed angles intercept the same arc. They're the same angle. They're congruent to each other. They're equal. So 24 and 24. Okay. Questions with any of the stuff from yesterday? Again, those theorems are directly in the book, what I pulled from, and I'll make sure I'll put those in the actual notes for the website. I think I'm still posting video from yesterday. So, all right, we're good though? Perfect. All right, let's go to the new ones today. Let's go to 10.8 and 10.9 today, and we're going to try to prove them. That's pretty much what we're going to kind of end today. We'll try to do examples of these, but that's kind of where we'll stop, because we don't have a lot of time today, but I don't want to take everything today just to do these two, so.
Order, are these ones, does 10.8 or 10.9 have a name or no?
No, there's no names on these. I think 10.8, if I remember right, I think it was also a corollary from previous textbooks I've had. So it's not even important enough to be a theorem in other textbooks, that's why it probably doesn't have a name. But your book felt it needed to be a theorem, so theorem 10.8. Okay, this is going off of the last one. If an inscribed angle intercepts, if an inscribed angle intercepts a diameter or semicircle, then its measure is 90 degrees. Now this is a little bit paraphrased in the book. The book had slightly different wording than me. They used the word if and only if, so they actually made it a biconditional. The words in the book said, an angle that intercepts a diameter or semicircle is a right angle if and only if the triangle's like a right triangle or something like that. It was something silly. It was just basically talking about 90. I just didn't like the way the book had it. I didn't like the wording. So inscribed angle is intercepting a diameter or a semicircle. So it's the same idea that you still have a circle, but now we have to deal with the diameter. So the diameter, remember, goes right through the center, so let's call this the center. It's a terrible center, but let's call it the center. And we have an angle that's intercepting it. So an inscribed angle that's looking across the picture at my... What they're saying is that this angle has to be a right angle. It has to be 90 degrees. So it's basically a right triangle. That's why the book kind of uses those words. So inscribed angle intercepts a diameter or semicircle, then its measure is 90 degrees. Well, if this is a true diameter, what's the measure of the diameter? 1/8, right? It's a straight line. That's what makes a line right at diameter straight across. It's 180. So this would actually be considered a central angle, the 180. So that's a central angle. It's right at the center of the circle. It can go out and it can go to the arc. We can always label central angles on the outside. So that would be 180 degrees because that is a true semicircle from here to here. Let's call this A and B. And let's put another point on it. Let's call it point D. So the measure of ADB, the actual arc, that is a semicircle arc, right? They have used 3 letters. The measure of it is 180. Because remember, the central angle is the measure of the arc that we look at. So the whole arc here is 180. Well, the idea is that when you drag an angle across the picture, so it's not central anymore, but you go to inscribed, where you drag it from the center to the outside, it's now half. Well, what's half of 180? 90. And that's why this thing works. That's why you get 90 degrees at that spot. Well, the reason why this is so important, why I want to stress like this whole 90-degree idea. This is the only way you're having a right angle inside of a circle. That's the only way that can happen. That if the one wall actually is the diameter and then the other 2 walls aren't. That's the only way you're getting a 90-degree angle. Otherwise, everything else won't work out that way. So let me explain. Like some people are like, well, can't you just do something like this where you make a right angle like that? Okay, it still turns out to be that's the diameter. Because of the way that this angle has to work, that whatever this arc is over here, this angle has to be half of it. So the only way that this could be 180 so that you take half of it is if this is the actual diameter right here. So this would be the perfect diameter on the inside. So it's like there's no other way you could draw the right triangle inside the circle that would actually make all 3 parts fit, like laying on the circle itself, and make a right angle. So that's why this one is so important. That is the only way you could draw a right triangle in a circle that's totally inscribed, that every single vertex lands on the circle. It's kind of a rarity. But from that, you can do Pythagorean theorem, you can figure out pieces, you can figure out parts, you could figure out area of the shaded part if they did something like this where they had their right triangle drawn and they wanted you to find the area of this part. That would be a really good ACT question where they could ask, what would the area of the shaded part be? Because you'd have to find the area of the half circle. The area of the circle is pi r squared. That's how you find the area of a circle. We'll go back into that at the very end of the section. But what you do is you find the area of the triangle, and then you subtract it from the half circle. This gives you the area of the full thing. Okay. But that's kind of the idea. Mr. Orman, can I help you?
Do I leave a backpack in here this morning?
You want to find a backpack? Is it in here somewhere?
No, I was thinking a black one.
That's mine.
Okay. I've checked like every classroom.
Sorry.
Huh.
Okay.
Thank you.
Yep.
Tia, did you check your vehicle yet?
Well, I had it this morning, so I was doing my homework. I got all the homework done. Then I went to the meeting. library. And my backpack's dying. Well, that's what happened.
Alright. Yeah, that's my bag. I thought you'd get saw another bag. Alright. Okay. Everyone get the kind of the idea how this one works? That basically what you're seeing there, that's the proof. I know that's really short and simple, but in this whole concept that it's half the arc that it looks at. Well, if the arc is 180, you take half of it. So this is nice to kind of see a review of how to do arcs again. That if they use 3 letters, that means a larger arc or a semicircle, major arc. I guess that's a better word. So, larger. But yeah, half. Okay, that was 10.8, pretty straightforward. We're going to look at an example of this at the very end of class today, but I wanted you to get the idea of what we're doing here. We're taking half of the arcs, okay? All right, last theorem here, and then we'll get to some examples where we can actually try to talk about how to use this. We'll do examples of what would be in your homework eventually. We're not getting homework or anything like that today, we're just doing some notes. All right, last one here, Theorem 10.9. And again, in my other geometry textbooks, this is also corollary, so it doesn't have a name. If a quadrilateral is inscribed in a circle, then its opposite angles are supplementary. So I'll let you write that down. We'll talk about it. We'll draw it. We're inscribing a quad in a circle. We're going to talk about the opposite angles. Quad is inscribed in the circle, then its opposite angles are supplementary. Okay, so let me draw the mock picture here. So we have a circle. We're going to draw a quad on the inside, so we're going to have a 4-sided figure. And to be perfectly inscribed, that was where we had in the very first section of chapter 10. All the vertices have to land on the circle itself. All 4 vertices have to land. Now, it didn't say what type of quad, so don't feel like this has to be a perfect square. It can be any type of quad as long as the 4 vertices actually land on the circle itself. Well, what this one is saying is that the 2 angles that are across from each other, so it didn't matter which pair you pick. I'll pick A and B here. I'll put A and B here and here. These 2 angles, they're different, right? They're not equal, but what they said in this is that they have to be supplementary. So the measure of angle A, and if you add that to the measure of angle B, you will always get 180 degrees. That's what it means to be supplementary. If they're crossing each other, they have to add up to be 180 no matter what. They're not equal, but they add to make 180. And that would be the same for the other 2 if I label those. Let's label those, let's call it C and D. We won't get real creative here. C and D. Same idea, that C and D would have the same rule, that the measure of angle C plus the measure of angle D, you're going to make 180. Okay, now the goal is to prove this. Like, why is it going to add up to be 180 every single time? That's what I want to show you. Alright, this one's going to take a little bit of algebra skills, so hopefully you can kind of remember a lot of those things you learned in Algebra 1. That will hopefully help you out. Okay. Alright. Let's start with the fact, what do circles add up to be completely? What's the angle? Okay, 360. So if we added up the entire circle, so if I use this arc right here, and I added it to this one, you'd get a total of 360. That's what makes a full circle. So the measure of arc DBC, that large arc, that's a major arc, and you add that to the other arc, CAD, that you're going to get 360. You're going to add up the big circle, everything, DBC, CAD. So you're going all the way around and get 360. Everyone kind of figures that out. Now, I'm going to use that concept. Do you agree that that's an equation? Like it has an equal sign, it has two things that are balanced. I can do, in algebra class, I can do anything I want to both sides. I can add numbers to both sides, I can multiply to both sides, I can divide, I can do anything I want to that equation, as long as I do the same number to both. So I can magically add 4 to both sides. I could multiply by 10. Or, what if I divided both sides by 2? So if I divided both sides by 2, so dividing by 2 is like the same as multiplying by half. It's dividing by 2. So I'm going to divide both sides by half. The whole side, whatever this adds up to be, I'm going to divide it in half and I'm going to cut 360 in half. You agree that those are still equal to each other? Yeah, it's a property of equality, right? It's actually called the division property of equality, or multiplicative, the way that I'm doing it. Okay, now why I can do this, and this is where the algebra 1 comes in. I can distribute the half. When you have a parenthesis with a number up front, you're allowed to distribute over it. So I'll distribute the half, so that'll be half measure of DBC, and add that to half the measure of CAD. So when you distribute, and what's half of 360? 180. Okay, so we get 180 here on that side because it's divided by 2. Okay, so far so good. I distributed and multiplied. Now, all I need to do is substitute what those are. DBC, if you look at this picture, DBC, that's like a major arc or a semicircle of some sort. DBC is the arc from D to B to C. All right, so let me highlight that. Let's get rid of this. The bubble I have right here, that's DBC. Okay, that's this full arc. Do you agree that this angle, angle A, is looking at that arc? Okay, it's looking at this is an inscribed angle. It's touching a circle, and the actual angle itself is looking at that entire arc. So what we talked about in these previous theorems, Theorem 10.6 and 10.7, is that when you have an inscribed angle that looks at an arc, this angle is half of the arc that it looks at. So that arc over there was 100 degrees. I could cut it in half, so this would be 50. Well, that's what I have here. I have half of DBC. So that would be the measure of angle A. This whole thing is just angle A. Because if I took half of it, that would be this angle right there. The one across from it. And the same thing with the other one. So let me get rid of that bubble. CAD, that's going this way, it's that angle, that's that arc. I'm going to take CAD, I'm going to take half of it. Well, half of this arc is the angle that looks at it, this angle right here. That is an inscribed angle, it is looking at this entire arc, CAD. So if you took half of it, that would be angle B. So if I'm going to use red, this would be angle B. And this 180 would hop it down. That proves it. The opposite angles have to add up to be 180. Opposite angles have to be 180. So no matter what they are, no matter what the numbers are, you can always find the angles across a rectangle or a square or a quad if it's in a circle. You know, we've had other properties about parallelograms and stuff, but this, if it's in a circle, the opposite angles have to add up to be 180, like this. So somebody just make up a number, please. 6. Okay, so if this is 6, then this angle that's across from it has to be 174. No, it may not look like it, because what we just talked about is that these have to add up to be 180. So if you have one, you can find the one across. That's what this theorem is saying. Make up a different number.
73.
What was the number?
73.
73. Okay, 73. So that's 73. This angle across from it has to be 107. They have to add up to be 180. That's the only way that it works. That's the concept. And now we're at 12. That was another. We'll use 12 as well. But Does everyone understand the concept? For some reason, this problem right here, there, you're looking at it, is the number one question people miss on this next test we take over chapter 10. In all the years, I've been teaching geometry a lot of years, this problem messes people up for some reason. That one, you're looking at how to do it. That's like the picture I showed you, and you just have to find the number across from it. But, because everyone always thinks, oh, they're equal, and they transfer numbers across, and they don't get anything right. The angles opposite of each other have to add up to be 180. So if you need to take 2 minutes right now, draw that picture and make sure you label it. So that's how you do this problem. I don't know why. It's the number one question to miss on my next test. I don't know why. It's just people can't remember it. Again, I can put any numbers in, but again, if the quad is inside the circle, that is the property that has to work. It has to work that way. Okay, we're good with 10-9? Now, type of homework problem you could have for this one, because the whole goal is to talk about the examples, like what are homework problems we could use? Or what are the problems where we need to get eventually used to that you'll possibly see as early as tomorrow. I don't know if we'll get homework tomorrow, but as early as tomorrow would be the earliest I can do it. So let's talk about it. So, Theorem 10-9. The type of problem that you could definitely see, be they have a circle, they have the quad of some form plugged in there. They could plug this as a 2x plus 1. This is a 3x plus 4. And they ask you to solve. They say solve for x, find your angles. So maybe this is angle A, this is angle B, and they ask you to find the angles for those two. So find x, find angle A, find angle B. Fair enough. Okay, so here's how you do it. What should those two add up to be? 180. Okay, so we know that they're not equal, they have to add up to be 180. So that plus the other one, 3x plus 4, has to make 180. So you add these together, that's 5x's, that's a 5. If I add those other numbers together, 180, there we go. Subtract that across, so we get 5x equals 175 divided by 5. So 335, something like that, for x. Why did my division right in my head? And then you could take that 35, because that's my x, that's what we just found. So this question mark is 35. Now you could take, and you could plug it back in, and find what angle A is and what angle B is. Really, you only have to find one of them, because if you have one, you could always go find the other one. So I'll just take this 35 and I'll plug it in here. So 2 times 35 plus 1, what is it, 71? Did I do that right? So that's 71, so then that means this angle up here has to be 109. If I plug the 35 in, it should have proved that. It should be a 109. So that's the only way it adds up to be 180. Questions, comments, concerns? Perfect. Last example of the day, and it's based on the last theorem. This is my absolute last problem of the day.
Wait, I have a question.
Yes.
So if one of them's 90, and then so that means the other one would be 90.
Yeah, it has to be.
Other two would be 90.
In theory, yeah, the other two would have to be 90 because they still have to add 360. But it could be yeah, they would pretty much have to be. If you have 90s in one corner, you pretty much have 90s in the rest. And so I don't think I can think of another way it could be. That'd be a weird looking picture. I think they would have to be 90s in that case. Okay. All right, last example of the day. Using 10-8, that was the theorem I just showed you earlier with the whole right angle thing. So theorem 10-8. One of the questions that I know in the book for the homework was something like this. They said this is a 3x plus 2. This is a 4x plus 5. I'm just making up numbers. Okay. If that's the case, like if this is what they give you, and they say, like, they actually show that this is like the center, then that means this has to be a right triangle, because that's a diameter, and that's the only way you can draw a triangle. And the idea is that, what does the triangle have to add up to be? 180. So you could add up all three of these to make 180. Or you could, these two have to add to be 90. But bless you, whatever's used. But you'd have to add those together. And so this is how I would do it. I would add these together to make 90. Because 90 plus 90 makes 180. Or you could add up all three to make 180. So you could add these, that's 7x plus 7 equals 90. Subtract that over, you get what, 83. Divide by 7. And you get some weird number, but you get the idea. It's like 10 point something. Actually, almost over 11 point something. Okay, questions, comments about what you have to do on that type of problem? Okay, just, they don't give you a lot, like they didn't give you the 90, you just had to know that it was 90 because of this theorem 10a. That the only way you could draw a triangle that goes through the diameter, through the center, is if it was a right triangle. Okay, we're good though? Okay, done for the day. Very nice, very easy. Okay, just a reminder to